Have you ever made a choice that changed everything? Turned left instead of right? Said yes instead of no? Stayed when you could have gone? Think about that moment when you stood at a crossroads and wondered what would have happened if you had chosen differently. We tell ourselves that those other paths simply vanish, that they're nothing more than ghosts of possibility. But what if they don't vanish at all? What if every choice you didn't make is just as real as the one you did, playing out somewhere beyond the reach of your awareness? In 1957, a graduate student named Hugh Everett III proposed something that his professors thought was absurd. He suggested that quantum mechanics, the most successful scientific theory ever created, was trying to tell us something extraordinary about the nature of reality itself. When physicists measured quantum particles and watched them collapse into definite states, they assumed the other possibilities simply disappeared. Everett said no. He said they all happen, every single one. Each outcome becomes real in its own separate universe, branching away from ours in a vast cosmic tree of possibility. His professors hated it. His career suffered. But the mathematics worked flawlessly. This is not science fiction. This is not speculation. This is what happens when you take the equations of quantum mechanics seriously and follow them to their logical conclusion. For decades, physicists tried to dismiss the many worlds interpretation as philosophical excess, as mathematics run amok. They couldn't. The theory refuses to die because nothing about it contradicts what we observe. In fact, recent developments have made it more compelling than ever. Something changed in the last decade. Multiple independent lines of evidence started pointing in the same impossible direction. The multiverse theory just got terrifyingly real. Right now, as you listen to these words, there might be countless versions of you making different choices in parallel realities that exist just as solidly as this one. That sounds like fantasy, but quantum mechanics has never been wrong. Not once. Every prediction it makes about how particles behave has been confirmed to extraordinary precision. The equations tell us that reality splits. We just haven't wanted to believe it. The evidence is becoming harder to ignore. Think about the universe you inhabit. Roughly 13.8 billion years ago, something happened that physicists call the Big Bang. Space itself began expanding, carrying matter and energy outward in all directions. But here's what most people don't realize. The very mechanism that drove that early expansion, something called cosmic inflation, naturally produces not one universe, but infinite universes. This isn't speculation. This follows directly from the mathematics of inflation, and inflation theory has been confirmed by extraordinarily precise measurements of the cosmic microwave background radiation. Alan Guth proposed cosmic inflation in 1980 to solve several puzzles about why our universe looks the way it does. His colleague Andre Linde later developed eternal inflation, showing that once inflation starts, it can never completely stop. It keeps creating new bubble universes forever. The measurements are specific. The Planck satellite, which operated from 2009 to 2013, mapped the cosmic microwave background with unprecedented precision. The data showed exactly the pattern of tiny temperature fluctuations that inflation predicts. Scientists measured a spectral index of roughly 0.965, matching inflationary predictions almost perfectly. They found no signs of cosmic strings or other defects that alternative theories predicted. Inflation passed every test. But inflation, when you work through its mathematics carefully, doesn't just create our universe. It creates infinite universes, each potentially with different physical laws. Here's where it gets strange. You might think that parallel universes are forever beyond our reach, impossible to detect or test. But quantum mechanics gives us a window. Quantum interference, the phenomenon where particles behave as if they're in multiple states simultaneously, might actually be different universes interacting with each other at the quantum level. David Deutsch, a physicist at Oxford, has argued that quantum computation actually performs calculations across multiple parallel universes. When a quantum computer processes information, it's not just manipulating bits in our universe. It's harnessing computational power from countless parallel realities. In 2019, Google announced that its Sycamore quantum processor achieved quantum supremacy, performing a calculation in 200 seconds that would take the most powerful classical supercomputer roughly 10,000 years. The quantum computer processed information in superposition, existing in multiple states simultaneously. Think about what that means. Where does the computational power come from? A quantum computer with just 300 qubits can perform calculations across more states than there are atoms in the observable universe. Deutsch argues there's only one place that computational power could exist: in parallel universes. This creates a problem for anyone who wants to dismiss the multiverse as untestable. We're already building technology that appears to draw on it. Quantum computers work. They demonstrate quantum interference effects that become more pronounced as we add more qubits. Something is interfering with the quantum states in our universe, creating the distinctive patterns we observe. The many worlds interpretation offers the simplest explanation. Those other computational paths exist in parallel realities. But there's another line of evidence, completely independent from quantum mechanics. It comes from cosmology and a puzzle called fine-tuning. The fundamental constants of nature, the numbers that determine how particles interact and how forces behave, appear to be exquisitely calibrated for the existence of complex structures like stars, planets, and life. Change the strength of gravity by just 1 part in 10 to the 34th power, and stars cannot form. Alter the strong nuclear force by a few percent, and atomic nuclei fall apart. Adjust the cosmological constant by 1 part in 10 to the 120th power, and space either collapses immediately or expands so fast that matter never clumps together. These numbers have no known reason to take the values they do. In the standard model of particle physics, they're free parameters that we simply measure and plug into our equations. The probability that they would randomly land in the narrow range that permits complexity is vanishingly small, so small that it demands an explanation. For decades, physicists have wrestled with this problem. Some invoke a divine creator who carefully tuned the constants. Others propose anthropic reasoning. We observe these values because we couldn't exist to observe anything else. But neither answer is satisfying scientifically. The multiverse offers a different explanation. If inflation creates infinite universes with different physical constants, then most of those universes are sterile and empty. But some, by pure chance, would have the right combination of values to produce stars and galaxies, and eventually, observers. We find ourselves in one of those rare universes not because it was designed for us, but because we couldn't exist anywhere else. The multiverse transforms the fine-tuning problem from an impossible coincidence into a statistical inevitability. Somewhere in the infinite ensemble of universes, every possible combination of constants exists. We're in one that permits our existence. Leonard Susskind, a physicist at Stanford, has developed this idea extensively within the framework of string theory. String theory, which attempts to unify quantum mechanics and gravity, predicts that the universe has extra dimensions beyond the 3 of space and 1 of time that we experience. These extra dimensions can curl up in different ways, and each configuration produces different physical laws in our familiar 4 dimensions. The number of possible configurations is staggeringly large. Susskind estimates roughly 10 to the 500th power different possible universes, each with its own set of physical constants. He calls this the string theory landscape. Now comes the troubling part. If the multiverse is real, what does that mean for science itself? The scientific method relies on making predictions that can be tested and potentially falsified. But if every possible outcome occurs in some universe, how can any theory be proven wrong? This is the criticism that makes many physicists uncomfortable with multiverse theories. If anything that can happen does happen somewhere in the vast ensemble of parallel realities, then the multiverse seems to explain everything and therefore explains nothing. But that criticism misunderstands how multiverse theories actually work. The many worlds interpretation of quantum mechanics makes specific predictions about quantum interference patterns, decoherence times, and the behavior of quantum computers. Eternal inflation predicts specific patterns in the cosmic microwave background and makes testable claims about the large-scale structure of our observable universe. The string theory landscape predicts relationships between different physical constants that could potentially be tested. These theories are constrained by observations. They make predictions. They can be wrong. Something else is happening that makes the multiverse more testable than critics suggest. In 2007, cosmologist Laura Mersini-Houghton made a striking prediction. She argued that if our universe is one bubble in a larger multiverse, then other bubble universes should have left imprints on ours through quantum entanglement in the very early universe. Specifically, she predicted that the cosmic microwave background should show a large cold spot, an anomalous region where the temperature is significantly lower than the surrounding area. A cold spot of roughly the size and magnitude she predicted had already been observed in 2004 by the Wilkinson Microwave Anisotropy Probe, but its significance wasn't fully appreciated until her prediction. The cold spot is real. It spans roughly 1.8 billion light-years across and is roughly 70 microkelvins colder than the surrounding cosmic microwave background. That might not sound like much, but in the extraordinarily uniform cosmic microwave background, it's a massive anomaly. Statistical analysis suggests that the probability of such a cold spot arising by chance in the standard cosmological model is less than 1 in 50. Something caused it. Mersini-Houghton's multiverse explanation that it represents a region where another bubble universe collided with ours or left a quantum entanglement signature is controversial but has not been ruled out. The implications are staggering. If the cold spot is evidence of another universe, then we've detected the multiverse. We've found its fingerprint in the oldest light in our cosmos. Other anomalies in the cosmic microwave background might also be evidence of parallel universes. There's an unexpected alignment of large-scale structures called the axis of evil, though that dramatic name simply refers to the puzzling alignment of the quadrupole and octupole moments in the cosmic microwave background. There are also hints of large-scale flows of galaxy clusters, moving in coordinated patterns that suggest something beyond our observable universe is pulling on them. In 2008, Alexander Kashlinsky and his team analyzed the motion of roughly 1,400 galaxy clusters and found that they're flowing in a coordinated direction at speeds of roughly 1,000 kilometers per second. They called this the dark flow. The motion extends to distances of at least 2.5 billion light-years. Something beyond the observable universe appears to be pulling on these clusters. The most straightforward explanation is that there's a massive concentration of matter outside our cosmic horizon. perhaps another region of the multiverse with different density properties. The dark flow remains controversial, with some later studies questioning its existence, but other groups have found confirming evidence. Think about this in terms of your own life. You look around and assume that what you see is all that exists. But there are other cities beyond your horizon, other countries, other continents. You know they're real because people travel between them, because you can see their effects on trade and weather and culture. The dark flow might be similar. We can't directly see what's beyond our cosmic horizon, but we can measure its gravitational influence on the matter we do see. If it's real, it's evidence that something exists beyond the boundary of our observable universe. Now scale that feeling up to cosmic proportions. Our observable universe extends roughly 46 billion light-years in all directions. That's the distance that light has had time to travel since the Big Bang, accounting for the expansion of space. But there's no reason to think the universe stops there. Inflation theory suggests that the full universe is vastly larger, perhaps infinite. We're trapped inside a bubble of visibility, unable to see beyond the cosmic horizon. Other regions exist out there, possibly with different physical properties. The multiverse might not be some abstract theoretical construct. It might be as real and physical as the parts of Earth that you've never visited. This connects to something even stranger. In 2012, scientists at the Large Hadron Collider discovered the Higgs boson, confirming the last missing piece of the standard model of particle physics. But the Higgs boson's mass created a new puzzle. It weighs roughly 125 billion electron volts. That mass is peculiar because quantum corrections should drive it up to much higher energies, close to the Planck scale at 10 to the 19th billion electron volts. Something must be cancelling out those quantum corrections with extraordinary precision. This is called the hierarchy problem. One solution to the hierarchy problem involves supersymmetry, a theoretical framework that predicts each known particle has a heavier partner particle. The supersymmetric partners would provide exactly the right corrections to keep the Higgs mass low. But the Large Hadron Collider has found no evidence of supersymmetry despite extensive searching. The theory predicted that supersymmetric particles should appear at energies the collider has already explored. They haven't. This has led some physicists to reconsider whether supersymmetry is the right explanation. It's also led them to take the multiverse more seriously. Here's why it matters. If the multiverse is real and different universes have different Higgs masses, then we find ourselves in a universe where the Higgs mass permits complex structures for the same anthropic reasons that explain the fine-tuning of other constants. The Higgs mass doesn't need a deep theoretical explanation. It simply needs to fall within the range that permits observers to exist. Most universes in the multiverse would have Higgs masses that lead to immediate collapse or prevent atoms from forming. We're in a rare universe where the value permits life. This is not a satisfying explanation to many physicists who want to derive the Higgs mass from first principles. But it might be the correct one. The data pointing toward the multiverse comes from multiple independent directions. Quantum mechanics naturally produces branching realities. Cosmic inflation naturally produces bubble universes. String theory naturally produces a vast landscape of possible laws. Fine-tuning naturally finds explanation in observer selection across many universes. Anomalies in the cosmic microwave background might be direct evidence of other universes. The hierarchy problem might require anthropic reasoning across a multiverse. None of these arguments alone is conclusive, but together they form a pattern. Watch what happens when you try to avoid the multiverse. You need to explain quantum interference without many worlds, which requires adding collapse mechanisms to quantum mechanics that have never been observed and that create new theoretical problems. You need to explain cosmic inflation without eternal inflation, which requires fine-tuning the initial conditions in ways that seem arbitrary. You need to explain fine-tuning without a multiverse, which leaves you with unsatisfying appeals to design or brute luck. You need to explain cosmological anomalies without invoking anything beyond our universe, which requires increasingly contrived astrophysical scenarios. The multiverse might be the simplest explanation that fits all the data. That sentence probably sounds backwards. How can infinite parallel universes be the simplest explanation for anything? But simplicity in science doesn't mean intuitiveness. It means minimizing the number of assumptions and free parameters in your theory. The many worlds interpretation of quantum mechanics is technically simpler than collapse theories because it doesn't add any new mechanisms to the Schrödinger equation. It just takes the equation seriously and follows where it leads. Eternal inflation is simpler than single universe inflation because it doesn't require carefully tuned conditions to stop inflation everywhere at once. The multiverse is theoretically elegant even if it's conceptually overwhelming. This raises an uncomfortable question. If parallel universes exist, do they contain parallel versions of you? The answer depends on which kind of multiverse we're discussing. In the quantum, many worlds interpretation, yes. Every quantum measurement that could go different ways produces branches where each outcome occurs. There are versions of you where different neurons fired in your brain, leading to different thoughts and choices. These branching universes are extraordinarily similar to ours at the macroscopic level, because most quantum events don't cascade up to affect human-scale decisions. But some do. In some branches, you made different choices at key moments in your life. In the bubble universes produced by eternal inflation, the answer is more complicated. Most bubbles have different physical constants and would be completely alien environments where atoms don't form or stars don't shine. But in an infinite multiverse, every possible configuration occurs infinitely many times. There would be bubble universes with exactly the same laws of physics as ours. Given enough space and time, the same patterns would repeat. The same planets would form. The same evolutionary paths would unfold. There would be Earths essentially identical to this one, with versions of you living lives essentially identical to yours. The mathematics here is straightforward, but the implications are vertiginous. In an infinite space with finite possible configurations of particles, repetition is inevitable. Max Tegmark, a cosmologist at MIT, has calculated the distances involved. He estimates that an identical copy of you would exist roughly 10 to the 29th meters away. That's a 1 followed by 10 to the 29th zeros. The observable universe is only roughly 10 to the 26 meters across. Your identical twin exists, but impossibly far beyond any horizon you could ever reach. In fact, there would be infinite identical copies, each living the same life, having the same thoughts at this exact moment. Think about that for a moment. There are versions of you out there who made the choice you didn't make. They're wondering about you too, in a sense, wondering about the paths they didn't take. Except they're not really wondering about you specifically because they don't know you exist. They're wondering about hypothetical alternate versions, not realizing those versions are just as real as they are. This is what the multiverse implies when you follow it to its logical conclusion. Every version of every possible life plays out somewhere. But here's where it gets uncomfortable. If every possible outcome occurs, what happens to meaning? If you make a good choice here but a bad choice in another universe, does the good choice matter? If you succeed in this universe but fail in countless others, does success have significance? These aren't just philosophical questions. They touch on how we understand our own existence and choices. The multiverse threatens to render everything meaningless through an overabundance of meaning. Every story plays out every way. Every choice leads to every consequence somewhere. Some physicists argue that meaning persists precisely because you only experience one branch. You don't have access to the other versions of yourself. Your choices shape your experienced reality even if other outcomes occur elsewhere. The you reading these words right now exists in a particular branch of reality, and your choices determine how that branch evolves. The existence of other branches doesn't diminish the reality of your experience in this one. You are still making real choices with real consequences in your local corner of the multiverse. Understanding this requires grappling with how we detect things we cannot directly observe. Science is full of such inferences. You cannot see atoms directly, but you can measure how light scatters off them. You cannot see black holes directly, but you can measure how they bend space-time and trap light. You cannot see dark matter directly, but you can measure its gravitational effects on galaxies. The multiverse might be similar. We may never directly visit another universe, but we can potentially measure its effects through quantum interference, through cosmological anomalies, through the unexpected properties of particles. In 2016, a team led by Rangaram Chari at the California Institute of Technology analyzed data from the Planck satellite and found what appeared to be evidence of another universe bumping into ours. They detected an excess of brightness in certain regions of the cosmic microwave background that could be explained by another bubble universe with more matter interacting with ours during the early stages of inflation. The signal was subtle and near the threshold of statistical significance. Chari estimated roughly a 4.6 standard deviation detection, just shy of the 5 standard deviation threshold that physicists typically require to claim a discovery. The finding remains controversial and requires confirmation, but the fact that scientists are even looking for such signals represents a shift in how we think about the multiverse. A generation ago, it was pure theory. Now researchers are developing specific tests and searching real data for signatures of parallel universes. In 2018, a team from the UK and Australia proposed that the multiverse might be detectable through disk-like patterns in the cosmic microwave background, left by collisions between bubble universes. They searched the Planck data and found 4 candidates, though again, at borderline statistical significance. These studies are pushing the boundaries of what we can currently observe. The pattern reveals itself across multiple scales. At the quantum level, particles exist in superposition across many states until measured. At the cosmological level, inflation produces many bubble universes with different properties. At the mathematical level, string theory produces a vast landscape of possible laws. The multiverse isn't one idea, but a convergence of ideas from different areas of physics, all pointing in the same direction. That convergence makes it harder to dismiss. If only quantum mechanics suggested parallel universes, you might chalk it up to interpretational excess. But when cosmology and string theory independently arrive at similar conclusions, the case becomes more compelling. What happens next is both exciting and frustrating. New quantum computers will probe larger and larger superposition spaces, potentially revealing more about the nature of quantum interference and whether it truly represents interaction between parallel worlds. New cosmological surveys will map the cosmic microwave background and large-scale structure with greater precision, potentially revealing more anomalies that hint at other universes. New particle accelerators might discover new physics that either supports or undermines the string theory landscape. The evidence for or against the multiverse will become clearer in the coming decades. But there's also a possibility that the question remains forever, just beyond our reach. If other universes are causally disconnected from ours, separated by unbridgeable distances or different sections of the quantum wave function, then direct confirmation might be impossible in principle. We might forever be in the position of making inferences from indirect evidence, never quite certain. That uncertainty bothers many scientists. It feels unscientific to believe in something we can never definitely confirm. But science has always dealt with entities and phenomena at the edge of observability. The multiverse might simply be the latest example. Consider what this means for how we understand our place in reality. For thousands of years, humans have undergone a series of demotions in cosmic significance. We learned that Earth is not the center of the solar system. We learned that the Sun is an ordinary star among billions in our galaxy. We learned that our galaxy is one among trillions in the observable universe. We learned that the observable universe might be a tiny fraction of a much larger cosmos. Now, we're potentially learning that our entire universe might be one bubble in an infinite foam of universes, and that even our choices and experiences might be repeated infinite times across parallel realities. Each demotion was initially disturbing and then became a source of new understanding. The Earth's motion around the Sun explained the seasons and planetary orbits. Our position in a typical part of a typical galaxy explained why the Milky Way looks the way it does. The vast number of galaxies explained the darkness of the night sky, despite the universe being filled with stars. The multiverse might similarly explain puzzles that otherwise seem intractable. Our apparent insignificance keeps revealing deeper patterns about how reality is structured. This is not just cosmology, this is ontology, the study of what exists. For most of human history, existence seemed straightforward. The things you can see and touch exist. Everything else is imagination or mathematics. But 20th century physics revealed that the category of things that exist includes much more than what we directly perceive. Quantum fields permeate all of space. Virtual particles constantly pop in and out of existence. Curved space-time determines how matter moves. Dark matter outweighs ordinary matter 5-to-1 in the universe, despite being invisible. Dark energy comprises roughly 68% of the universe's total energy, despite being undetectable, except through its effect on cosmic expansion. The multiverse might simply be the next expansion of our ontology, our catalogue of what exists. The pieces are starting to fit together in unexpected ways. Quantum mechanics was developed in the early 20th century to explain atomic spectra and the behavior of subatomic particles. Cosmic inflation was developed in the late 20th century to explain the uniformity and flatness of the universe. String theory emerged from attempts to describe the strong nuclear force and later evolved into a candidate theory of quantum gravity. These frameworks were developed independently to solve different problems. The fact that they all point towards some form of multiverse is either an extraordinary coincidence or a hint that the multiverse is a real feature of nature that different approaches are converging on. But the story doesn't end there. The multiverse creates new puzzles even as it solves old ones. One of the most troubling is called the measure problem. In an infinite multiverse, everything that can happen happens infinitely many times. How do you calculate probabilities in such a framework? If there are infinite universes where you make choice A and infinite universes where you make choice B, what does it mean to say one outcome is more likely than the other? Infinity divided by infinity is undefined. You need some way to compare infinite sets to make predictions. This is not just a mathematical technicality. It threatens to make the multiverse unpredictive and therefore unscientific. Physicists have proposed various solutions to the measure problem. One approach involves comparing the density of different types of universes rather than their absolute numbers. Another involves considering only universes within a certain region of the quantum wave function or a certain space-time volume. Another invokes anthropic reasoning. We should consider only universes that can support observers like us. None of these solutions is entirely satisfactory, and the measure problem remains an active area of research. The multiverse might be real, but figuring out how to make precise predictions within a multiverse framework is still a work in progress. There's also the question of testability limits. Even if the multiverse is real, there might be aspects of it that are forever beyond our ability to test. If quantum branches decohere completely and never interact again, we might never be able to confirm that other branches exist beyond the evidence from quantum interference. If bubble universes are separated by vast expanses of inflating space that expand faster than light can cross them, we might never detect them except through rare collisions in the early universe. Some versions of the multiverse might be testable, while others remain speculative. This creates a philosophical problem for science. Does a theory count as scientific if it makes some testable predictions, but also includes components that can never be tested? The many worlds interpretation makes testable predictions about quantum interference, but cannot test the existence of other branches directly. Eternal inflation makes testable predictions about the cosmic microwave background, but cannot test the existence of other bubbles directly, except through rare signatures. Are these theories scientific or not? The answer isn't clear-cut. Science has always involved some degree of inference beyond direct observation. The question is how far that inference can extend before it stops being science and becomes metaphysics. Nobody expected what came next in the 2010s. Multiple research groups began exploring whether quantum mechanics could be tested in ways that distinguish between different interpretations. For decades, physicists had assumed that the Copenhagen interpretation, many worlds, and other interpretations were empirically equivalent, that they made identical predictions and differed only in philosophical outlook. But some researchers began to question whether that's truly the case. If many worlds is correct and branches never truly disappear, then perhaps there are situations where quantum interference persists longer, or in different ways than collapse theories predict. In 2018, Howard Wiseman and colleagues at Griffith University proposed that many worlds makes different predictions than collapse theories when you carefully consider the nature of measurement and decoherence. They suggested that experiments involving very careful isolation of quantum systems might reveal subtle differences. The experiments are extraordinarily difficult because you need to prevent decoherence, the process by which quantum systems become entangled with their environment and appear to collapse. But if successful, they could potentially distinguish between interpretations that were long thought to be indistinguishable. This is where quantum technology becomes crucial. Modern quantum computers and quantum experiments can manipulate systems of many particles in superposition and measure subtle directly. It tells you that the wave function splits into multiple branches, but it doesn't specify the ontology, the physical nature of those branches. Some physicists argue that many worlds is really many minds, that the branching happens in the structure of observers rather than in physical reality. When you measure a quantum particle, your brain enters a superposition of different states, each perceiving a different outcome. The universe doesn't split. Your consciousness does, or at least the physical state of your brain does. This seems even stranger than many universes, but it might be what the mathematics is actually telling us. The line between mind and world becomes blurred at the quantum level. Think about the last time you made a difficult choice and couldn't stop wondering about the other option. That feeling of possibility, of paths not taken, might be a psychological echo of something physically real. In the quantum realm, those paths are taken. Every possibility branches off into its own reality. We experience only one branch, but the others exist in the structure of the universal quantum state. Your choice determines which branch you experience, but it doesn't eliminate the other branches. They continue evolving in parallel forever beyond your reach, but no less real for that. Now scale that up to everything that has ever happened. Every quantum event in the history of the universe, from the Big Bang to this moment, has been a branching point. The number of branches is incomprehensibly vast. Some physicists estimate that the quantum state of the universe branches roughly 10 to the power of 100 billion times per second. Each branch is a slightly different version of reality. Most branches are nearly identical to ours, differing only in microscopic quantum details. But some branches diverged long ago and are radically different. In some branches, the asteroid that killed the dinosaurs missed Earth. In some branches, you don't exist because your parents never met. The implications ripple outward into every area of human thought. If many worlds is correct, then determinism and free will might both be true in a sense. The universe evolves deterministically according to the Schrödinger equation, with all possibilities unfolding. But from your perspective inside one branch, you make choices that determine which branch you experience going forward. Your choices are real and meaningful, even though all possible choices are made by different versions of you in different branches. This is not a comfortable resolution to the free will debate, but it might be the correct one. Something else was happening while physicists debated quantum interpretations. Cosmologists were pushing deeper into the implications of inflation. Alexander Vilenkin at Tufts University proved mathematical theorems showing that eternal inflation, once started, can never end. Even if inflation stops in one region, creating a bubble universe like ours, it continues in other regions, creating more bubbles forever. The process is self-sustaining. Some of the quantum fluctuations in the inflating space cause inflation to accelerate rather than slow down. Those regions then produce more fluctuating space, some of which accelerates further. The result is an infinite fractal tree of bubble universes, constantly branching and growing. The numbers here are staggering beyond human comprehension. It's not just that there are many universes. There are infinite universes. And because inflation never ends, new universes are being created constantly. The multiverse is not a static collection of bubbles, but a dynamically growing structure that becomes larger and more complex without limit. Every second, countless new bubble universes are born somewhere in the vast expanse of eternally inflating space. Each one potentially has different properties determined by how the inflaton field and other quantum fields settle into stable configurations. This connects to the string theory landscape in a direct way. When a new bubble universe forms, the extra dimensions in that bubble curl up into one of the 10 to the 500th power possible configurations. Which configuration actually occurs might be random, determined by quantum fluctuations during the bubble's formation. The result is that the multiverse samples the entire landscape of string theory. Every possible configuration of extra dimensions is realized somewhere. Every possible set of physical laws appears in some bubble. We live in one bubble where the configuration happened to produce laws that permit complex structures and observers. Calculate what this means for fine-tuning. The probability that a randomly selected universe from the string theory landscape would have constants fine-tuned for life is roughly 10 to the negative 120th power for the cosmological constant alone, and similarly small for other constants. But in an infinite multiverse that samples all possibilities, even probabilities that small become certainties. With 10 to the 500th power, different possibilities and infinite bubbles. Every configuration, including the ones fine-tuned for life, exists in vast numbers. The fine-tuning problem disappears, or rather transforms into an observer selection effect. But there's a catch. This line of reasoning only works if you assume that we're typical observers in the multiverse. If most observers in the multiverse exist in universes very different from ours, then our existence here becomes puzzling again. Maybe most life evolves in universes with different constants that produce more hospitable environments. Maybe we're in an extremely atypical universe for some unknown reason. Without knowing what other universes are like and whether they produce observers, we can't assess whether anthropic reasoning actually solves the fine-tuning problem or just rephrases it. This is where the measure problem becomes acute. To make anthropic predictions, you need to know the relative frequencies of different types of observers in the multiverse. But in an infinite multiverse with infinitely many observers of every type, how do you calculate relative frequencies? You need some way to cut off the infinities and compare finite sets. Different cutoff procedures give different answers, which means the predictions depend on arbitrary choices about how to do the counting. This is unsatisfying. A truly predictive theory shouldn't depend on arbitrary choices. Some physicists argue this means the multiverse is not a scientific theory. If it can't make definite predictions about what we should observe, then it's not testable and doesn't belong in science. Others argue that we're still developing the right mathematical tools to extract predictions from multiverse theories, and that giving up now would be premature. The situation is analogous to early quantum mechanics, when physicists struggled to interpret the theory and make sense of its predictions. It took decades to fully work out the implications and develop the right mathematical framework. The multiverse might require similar patience. The answer changes everything if we can solve the measure problem. With a well-defined measure, the multiverse would make testable predictions about the distribution of physical constants, the properties of the cosmic microwave background, the existence of certain types of particles, and much more. We could use observations of our universe to test whether it fits the predicted distribution from multiverse theories. Early attempts to do this have yielded intriguing but inconclusive results. The cosmological constant seems to fit anthropic predictions reasonably well. Other constants are less clear. More work is needed. Meanwhile, quantum technologies continue advancing. In 2023, multiple research groups demonstrated quantum computers with over 1,000 qubits, far exceeding previous records. These machines can maintain quantum coherence for longer times and perform more complex calculations in superposition. Each advance makes quantum interference effects more pronounced and easier to study. If many worlds is correct and quantum computers truly harness parallel universes for computation, then we're building more powerful windows into the multiverse with each new generation of quantum hardware. The technical challenges are immense. Qubits are extremely fragile and easily disrupted by environmental noise. Maintaining quantum coherence requires near-perfect isolation and extraordinarily low temperatures, typically within a few thousandths of a degree of absolute zero. But progress is steady. Researchers are developing new types of qubits, new error correction codes, and new ways to shield quantum systems from decoherence. Within a decade or two, quantum computers might be powerful enough to perform calculations that classical computers couldn't match, even if they ran for the entire age of the universe. Watch what happens when you think about what that means. If quantum computers achieve what's called quantum advantage for practical problems, Proving their computational power comes from quantum effects that classical physics can't match, then we need to explain where that power comes from. The many worlds interpretation offers a clear answer: parallel universes. Other interpretations struggle to explain it without invoking hidden variables or non-local effects that seem contrived. The success of quantum computation might become indirect evidence for the reality of quantum branching. But even if many worlds is correct, there's a question of scale. How large can quantum superpositions become? In principle, the Schrödinger equation applies to everything, from single particles to entire people to the whole universe. But in practice, large objects decohere extremely quickly because they interact with so many particles in their environment. Your body is constantly exchanging photons and molecules with its surroundings. Each interaction entangles you with the environment and effectively collapses any quantum superposition you might be in. The branching happens, but it occurs so fast that you never perceive being in superposition. This is why you don't experience quantum effects in daily life. By the time a quantum event in your brain could influence your thoughts, decoherence has already occurred and you're in one definite branch. But the other branches exist. They're just separate from you, no longer able to interfere with your experiences. This explains why the quantum world seems so different from the everyday world. We live at a scale where decoherence is fast and pervasive. We never experience superposition directly, only its effects in carefully isolated quantum systems. Some researchers have tried to push the boundaries of how large an object can remain in quantum superposition. In 2019, a team at the University of Vienna demonstrated quantum interference with molecules containing up to 2,000 atoms. These molecules were large enough to have complex internal structures, but still small enough to isolate from environmental decoherence. The experiments confirmed that quantum mechanics applies even to these relatively large systems. As technology improves, researchers hope to demonstrate quantum effects in even larger objects, perhaps eventually visible to the naked eye. If quantum mechanics truly is universal and applies to everything, then, in principle, you could put a person in superposition. The technical barriers are impossibly high with current technology. You'd need to isolate someone from all environmental interactions, which is completely infeasible for anything larger than microscopic particles. But the theory doesn't forbid it. The Schrödinger equation applies to people just as it applies to atoms. You're constantly in superposition at the quantum level, with different branches experiencing slightly different versions of you. Decoherence just happens so fast that the branches separate before you notice. This creates a strange picture of personal identity. The you that exists right now is actually a collection of branches that haven't yet separated noticeably. Over the next second, those branches will diverge as quantum events in your brain produce slightly different neural states. Most of those branches will experience nearly identical thoughts and make nearly identical choices, but some will differ in subtle ways. And occasionally, at key decision points, the branches might differ significantly. The version of you reading these words is one branch among countless others, all equally real, all experiencing their own version of this moment. Here's where it gets uncomfortable again. If this is true, then death might not be what we think it is. In some branches, you live longer. In some branches, you die sooner. From the outside, observing all branches, you never truly cease to exist, because there are always branches where you continue. But from your inside perspective, in any given branch, you eventually die. The subjective experience of mortality remains even in a many worlds framework. You can't access the branches where you survive longer. Each branch is isolated by decoherence. This has led to disturbing speculations about quantum immortality. The idea is that from your subjective perspective, you only ever experience branches where you survive. When you die in one branch, your consciousness continues in the branches where you didn't die. Therefore, you subjectively experience something like immortality, always finding yourself in the branches where you're still alive, even as those branches become increasingly improbable. Most physicists reject this reasoning as confused about the nature of consciousness and probability, but it illustrates how strange the implications of many worlds become when you try to apply them to personal experience. The measurements that would settle these questions remain mostly beyond our reach. We can measure quantum effects in small systems. We can detect interference patterns and demonstrate that particles exist in superposition until measured. We can build quantum computers that exploit superposition for computation. But we cannot directly measure other branches of the wave function once decoherence has occurred. They've separated into non-interacting components. Quantum mechanics tells us they exist, but verification remains elusive. This is what makes the interpretation question so difficult. Compare this to how we've approached other unobservable entities in physics. We've never directly observed an individual atom, but we've built up overwhelming indirect evidence for their existence through chemistry, crystallography, scanning tunneling microscopes, and countless other methods. We've never directly observed the interior of a black hole, but the mathematics of general relativity gives us confidence in our predictions about what lies behind the event horizon. We accept these things as real because the theories that predict them are so successful in other domains. The same logic might apply to other branches of the quantum wave function, but there's a difference. Atoms and black holes exist in our universe. Other quantum branches are, by definition, separate from ours. They don't interact with us except through quantum interference, which becomes vanishingly small once decoherence occurs. The evidence for them is purely theoretical, coming from taking the Schrödinger equations seriously. That's more tentative than the evidence for atoms or black holes. It's more like the evidence for the interior of black holes, which also comes mainly from theoretical extrapolation rather than direct observation. Still, the mathematics is compelling. Think about whether mathematics can tell us what exists. That's a deep question in the philosophy of science. Some philosophers argue that mathematics is just a tool we use to describe reality, and that we shouldn't take mathematical structures as physically real unless they're directly observable. Others argue that if a mathematical structure is necessary to explain what we observe, then we should tentatively accept its physical reality even if we can't observe it directly. The debate goes back centuries and remains unresolved. The multiverse forces us to confront it again. The history of physics suggests that mathematics is a reliable guide to reality. Maxwell's equations predicted electromagnetic waves before anyone had detected them. Dirac's equation predicted antimatter before anyone had observed it. General relativity predicted black holes decades before evidence confirmed them. The Higgs mechanism predicted the Higgs boson 48 years before the Large Hadron Collider found it. When the mathematics is elegant and solves real problems, and when the theory that produces the mathematics is well tested in other domains, then we have reason to trust the mathematical predictions even when they seem strange or remain unverified. The mathematics of many worlds is elegant. It simply takes the Schrödinger equation as fundamental and applies it universally without adding collapse mechanisms. The mathematics of eternal inflation is well motivated by our understanding of quantum fields and the early universe. The mathematics of the string theory landscape follows from attempting to construct consistent theories of quantum gravity. These aren't arbitrary speculations. They're logical consequences of frameworks that have proven successful in explaining other phenomena. The multiverse might be real, even though it sounds like fantasy. Recent advances in cosmology have added new wrinkles. In 2024, the James Webb Space Telescope began detecting galaxies from surprisingly early times in the universe's history, some apparently forming just a few 100 million years after the Big Bang. Some of these galaxies appear more massive and mature than standard cosmological models predict at such early times. The observations are still being analyzed and debated, but they hint that our understanding of galaxy formation might be incomplete. Some cosmologists have suggested that these anomalies might be explained by different conditions in the early universe than we assumed, possibly related to how our bubble universe formed in the larger multiverse. The idea is that the quantum fluctuations that seeded galaxy formation in our universe might have had unusual properties inherited from the inflating space that gave birth to our bubble. If our universe formed through a particular type of phase transition as inflation ended, the resulting density fluctuations might differ slightly from what simple inflation models predict. These differences would show up as anomalies in the cosmic microwave background and in the early history of galaxy formation. The James Webb observations might be giving us clues about the birth of our bubble universe, offering an indirect window into the nature of the multiverse. But these ideas are speculative and controversial. Many astronomers think the early galaxy observations will be explained by conventional astrophysics once we better understand how the first stars and galaxies formed. Invoking the multiverse to explain every anomaly is bad science, a retreat into unfalsifiable speculation. The challenge is distinguishing between legitimate multiverse predictions that happen to explain observations and illegitimate appeals to the multiverse as a catch-all explanation for anything puzzling. The line is not always clear. This is why the measure problem is so important. Without a well-defined measure, the multiverse can explain anything and therefore explains nothing. With a proper measure, it makes specific predictions about what we should observe, and those predictions can be tested. The difference between a scientific theory and a so story is testability. The multiverse hovers on the boundary, tantalizingly close to being testable but not quite there yet. Whether it crosses fully into the realm of science or remains in the realm of metaphysics depends on progress in solving technical problems in cosmology and quantum theory. What's happening now is that multiple research groups are attacking the measure problem from different angles. Some are trying to find natural cutoff procedures that don't depend on arbitrary choices. Some are exploring whether the measure problem might have a unique solution once you properly account for quantum effects in eternal inflation. Some are investigating whether observer selection effects might provide a natural measure by focusing on the distribution of observers rather than the distribution of universes. Progress is slow but real. The problem might be solvable. If the multiverse becomes fully testable and is confirmed by observation, it will transform our understanding of reality in ways we're only beginning to appreciate. The universe we observe would be revealed as a tiny fragment of a vastly larger structure. The physical laws we've spent centuries uncovering would be local bylaws, specific to our bubble, not universal principles. Other bubbles would have different laws, different particles, different forces. The goal of fundamental physics would shift from finding the unique theory that describes reality to understanding the landscape of possible theories and explaining which one we find ourselves in. This shift is already happening to some extent. String theorists used to hope that string theory would uniquely predict the properties of our universe, that mathematics would force all the constants to take the values we observe. The discovery of the vast string theory landscape dashed that hope. Now the focus is on understanding the landscape itself, on figuring out which regions of the landscape produce universes hospitable to life, on explaining anthropically why we inhabit the particular region we do. It's a less ambitious program in some ways, but perhaps more realistic. The philosophical implications extend into theology and metaphysics. For centuries, religious thinkers pointed to the fine-tuning of the universe as evidence of divine design. The constants seem too precisely adjusted to be coincidental, suggesting an intelligent creator who set them with care. The multiverse undercuts this argument by showing how fine-tuning can arise naturally without design through observer selection across many universes. Most universes are sterile, but we necessarily find ourselves in a rare, hospitable one. This doesn't disprove the existence of God, but it removes one traditional argument for God's existence. Some religious thinkers have responded by embracing the multiverse as an even grander expression of creation. If God created not just our universe, but an infinite multiverse with unlimited diversity, that suggests a creator of extraordinary power and generosity. The multiverse becomes evidence of divine abundance rather than evidence against design. Others reject the multiverse as atheistic speculation designed to avoid the implications of fine-tuning. The debate continues, illustrating how scientific theories about cosmology inevitably intersect with deeper questions about meaning and purpose. For atheistic or agnostic thinkers, the multiverse offers a naturalistic explanation for existence that doesn't require invoking anything beyond the laws of physics. The universe, or rather the multiverse, simply exists as a brute fact. The laws of quantum mechanics and general relativity, applied consistently, produce eternal inflation and many worlds. Everything else follows. There's no need for a first cause or a designer. The multiverse is self-explaining in a sense, a structure that generates itself through its own internal dynamics. Whether this is truly satisfying depends on your philosophical intuitions about explanation and existence. There's also the question of whether the multiverse makes life more or less special. On one hand, if there are infinite universes and infinite versions of you, then you're not unique. Everything you do has been done infinite times before and will be done infinite times again. Your existence is generic, repeated endlessly across the multiverse. On the other hand, your subjective experience is still unique to you. The version of you reading these words right now exists only in this branch of this bubble. Other versions are separate and distinct. Your experience of consciousness, the feeling of being this particular person at this particular moment, belongs to you alone, even if countless similar experiences occur elsewhere. Maybe the question of whether life is special is ill-posed. Special compared to what? If you're asking whether humans are cosmologically significant, the answer has been no, since Copernicus. We're on an ordinary planet around an ordinary star in an ordinary galaxy in an ordinary part of the universe, possibly in an ordinary bubble of a vast multiverse. But if you're asking whether your individual subjective experience matters, the answer might still be yes. It matters to you, and perhaps that's enough. The multiverse doesn't diminish the reality of your experience. It just places it in a larger context. Time is running out to answer some of these questions with current technology. The cosmic microwave background has been measured with extraordinary precision by satellites like COBE, WMAP, and Planck. Future observations might refine measurements but won't radically improve them. If signatures of other universes exist in the cosmic microwave background, we've probably already seen them in the data. The challenge now is interpreting those signatures correctly and distinguishing genuine evidence of other universes from noise and foreground contamination. Similarly, quantum computers are rapidly improving, But there are physical limits to how large and complex they can become with current approaches. This creates some urgency in the field. Cosmologists worry that we might be in a golden age of discovery that won't last. The cosmic microwave background is pristine light from the early universe, and we've now mapped it comprehensively. Future observations will mostly refine what we already know. The large-scale structure of galaxies can be mapped more completely, but the fundamental puzzles, the anomalies and tensions that might hint at other universes, are already apparent in existing data. If we can't figure out what the data is telling us in the next few decades, we might not get another chance with better observations. The information is all there. We just need to understand it. Quantum experiments face different limitations. As we build larger quantum systems, decoherence becomes harder to prevent. There might be a practical upper limit to how many qubits we can coherently control before environmental interactions become overwhelming. We're approaching that limit, though it's unclear exactly where it lies. If many worlds is correct, quantum computers are already sampling parallel universes for computational power. Making them much larger might not add new conceptual information about the multiverse, even if it adds computational capability. But there are still unexplored experimental avenues. Some researchers are investigating whether quantum effects persist in biological systems, a field called quantum biology. If quantum coherence plays a role in photosynthesis, bird navigation, or even consciousness, then nature might have solved the problem of maintaining quantum effects at warm temperatures and in wet environments. Understanding how life exploits quantum mechanics could teach us new ways to probe quantum foundations and perhaps new ways to test interpretations like many worlds. In 2020, experiments suggested that quantum coherence does play a role in photosynthesis. Light harvesting complexes in plants and bacteria appear to use quantum superposition to efficiently transfer energy from chlorophyll molecules to reaction centers. The effect is subtle and controversial, but multiple independent experiments have found evidence for it. If confirmed, it means quantum superposition can persist in biological systems for timescales long enough to affect macroscopic outcomes. That's relevant to understanding where the quantum to classical transition occurs and whether many worlds applies to living systems. The implications for consciousness are even more speculative but tantalizing. If quantum effects play a role in how neurons process information, then your thoughts might literally exist in superposition, split across multiple branches of reality. Most neuroscientists are skeptical that quantum mechanics is relevant to brain function because neurons are too large and warm for quantum coherence to persist. But the brain is also extraordinarily complex and might exploit effects we don't fully understand. The question remains open. Roger Penrose and Stuart Hameroff have argued for decades that consciousness requires quantum effects in microtubules, structural proteins inside neurons. They propose that quantum superpositions in microtubules are maintained until reaching a threshold related to quantum gravity, at which point they collapse, producing moments of conscious awareness. The theory is controversial and lacks direct experimental support, but it illustrates how quantum mechanics might connect to consciousness. If they're correct, then your conscious experience involves quantum branching in a direct way. Most physicists think quantum mechanics and consciousness are separate issues. Quantum mechanics explains how particles behave. Consciousness is presumably explained by neuroscience and emerges from the complex interactions of neurons firing in patterns. The two domains don't need to intersect, but the measurement problem in quantum mechanics does involve consciousness in a subtle way. When you measure a quantum system from your perspective, it collapses into a definite state. But from the perspective of the wave function, it splits into branches. Where does your subjective experience of a single outcome come from if the wave function contains all outcomes? This is called the problem of probability in many worlds. The wave function splits into branches with different amplitudes determined by the Schrödinger equation. In the standard interpretation, those amplitudes give the probabilities of different measurement outcomes. But in many worlds, all outcomes occur. So what do the amplitudes mean? Why do you experience the outcome with high amplitude more often than the outcome with low amplitude if both actually happen? The answer might involve how probability works in a branching reality, but working out the details has proven difficult. Some researchers argue that the amplitudes determine how many branches correspond to each outcome. High amplitude means many branches experience that outcome. Low amplitude means few branches experience it. So from a random observer's perspective within the wave function, you're more likely to find yourself in a high amplitude branch, simply because there are more of them. This preserves the connection between amplitude and probability, but it requires treating the wave function as literally dividing into separate branches, which raises questions about ontology that many physicists find uncomfortable. The alternative is to give up on deriving probability from the wave function and simply accept that the amplitudes give probabilities as a fundamental postulate. But that feels unsatisfying. One of the appeals of many worlds is that it derives everything from the Schrödinger equation without adding extra assumptions. If you need to add probability as a separate postulate, you lose some of that elegance. The problem remains unresolved and is the subject of ongoing research and debate. These technical issues shouldn't obscure the larger picture. The multiverse has gone from speculation to serious scientific hypothesis in the span of a few decades. Multiple independent lines of evidence point toward it. The mathematics of quantum mechanics, cosmic inflation, and string theory all suggest that reality is vastly larger and stranger than the single universe we observe. While definitive proof remains elusive, the case is strong enough that dismissing the multiverse out of hand is no longer scientifically defensible. It might be wrong, but it's not crazy. The countdown continues toward observations that might settle the question. The next generation of particle accelerators, if they're built, might discover new physics that either supports or undermines the string theory landscape. The next generation of cosmic microwave background experiments might find clearer signatures of bubble collisions or rule them out definitively. Advances in quantum computing might reveal aspects of quantum mechanics that distinguish between interpretations. Within a few decades, we might know whether the multiverse is real or whether it's a mathematical mirage, elegant but empty. Until then, we're left in a state of uncertainty that's both frustrating and exhilarating. Frustrating because the biggest questions about reality might remain unanswered. Exhilarating because we're living in a time when such questions are even askable, when science has advanced far enough to seriously contemplate the existence of parallel universes. Previous generations could only speculate. We can measure, calculate, and test. Not definitively yet, but we're closer than ever. Think about what it means to live in this moment of uncertainty. You exist in a universe that might be one among infinite others. Your choices might spawn branches where different outcomes occur. The physical laws you take for granted might be local accidents, different elsewhere in the vast multiverse. Everything you think you know about reality might be a provincial view, valid only in your cosmic neighborhood. Or the multiverse might be wrong, and the universe might be singular after all, making your existence even more remarkable for occurring in the one reality that exists. We don't know yet, but here's what we do know. The universe is comprehensible, The same laws of physics that operate in laboratories on Earth apply to the most distant galaxies and the earliest moments after the Big Bang. Mathematics describes nature with uncanny precision. Experiments confirm predictions. Observations reveal patterns. When scientists make mistakes, other scientists correct them through the self-correcting mechanisms of peer review and replication. The process works slowly and imperfectly, but reliably, converging on truth. The pattern suggests humility. Every time we've thought we were special or central, we've been wrong. The Earth is not central. The Sun is not central. The Milky Way is not central. Our position in space is not central. Our moment in time is not special. The universe doesn't revolve around us. If the multiverse is real, it's the ultimate expression of that pattern. Not only is our planet ordinary, not only is our galaxy ordinary, but our entire universe with all its laws and constants might be ordinary. One possibility among countless others scattered across the vast landscape of the multiverse. But here's the strange thing. Despite our cosmic insignificance, we've managed to figure out where we are. We've mapped the galaxy, measured the universe's age and composition, probed the quantum realm, and contemplated parallel realities. Conscious observers on an ordinary planet have used mathematics and instruments to understand the largest structures in existence and the smallest scales of reality. That's remarkable. Even if we're not cosmologically central, we're epistemologically successful. We can know things about the universe that vastly exceed our immediate experience. This suggests that consciousness and intelligence, wherever they arise, have a special relationship with reality. The universe can be understood. The laws that govern it can be discovered. The patterns can be perceived. It doesn't matter that we're small or peripheral. What matters is that we're the right kind of structure, complex information processing systems capable of building models and testing them against observation. In a multiverse where most regions are sterile, the bubbles that produce observers are rare and precious, not because they're cosmologically significant, but because they're where the universe becomes aware of itself. Maybe that's the real implication of the multiverse. It makes existence less special in one sense, but more remarkable in another. If life and consciousness require such precise fine-tuning that they only arise in rare pockets of a vast multiverse, then the fact that you exist to contemplate these questions is staggeringly improbable from a purely physical standpoint. But from an anthropic standpoint, it's inevitable. Observers necessarily find themselves in the rare regions where observation is possible. You couldn't exist anywhere else. The multiverse creates the conditions for your existence by exploring every possibility, ensuring that some possibilities include you. This is not a satisfying explanation to everyone. It feels circular, explaining your existence by appealing to the fact that you exist. But it might be the only explanation available if the multiverse is real. The constants aren't fine-tuned by a designer. They're not determined by a deeper theory. They're simply environmental accidents, different in different regions, with observers arising only where the accidents happen to permit it. You're here because you couldn't be anywhere else, and there are infinite regions where you're not. That should be terrifying. It suggests that everything you are, everything you value, everything that feels meaningful exists only because of random quantum fluctuations in an inflating field 13.8 billion years ago. There's no deeper reason, no purpose, no design, just accidents stacked on accidents, with consciousness emerging as a side effect in the rare bubbles where the accidents happen to stack the right way. That's a bleak view. It drains significance from existence by revealing it as contingent on arbitrary conditions. But it's also liberating. If your existence is improbable and accidental, then there's no predetermined purpose you're failing to fulfill. You're free to create your own meaning, to value what you choose to value, to live however seems worthwhile to you. The universe doesn't care, but that means you're not beholden to cosmic purposes or grand designs. You're here by chance, and you get to decide what to do with that chance. The multiverse gives with one hand and takes with the other. It removes cosmic significance but preserves personal agency. These philosophical reflections are important because the multiverse isn't just a scientific theory. It's a worldview, a framework for understanding your place in reality. If it's true, then you need to grapple with what it means for how you live. Does it matter that other versions of you are making different choices in parallel realities? Does it change how you think about decisions, knowing that every possibility plays out somewhere? Does it affect your values, knowing that consciousness and intelligence are rare cosmic flukes rather than central features of reality? Different people will answer those questions differently. Some find the multiverse depressing, a revelation that we're even more insignificant than we thought. Others find it awe-inspiring, a demonstration that reality is vastly richer and stranger than we imagined. Some think it makes life meaningless. Others think it makes life more precious by revealing how improbable it is. There's no single correct emotional response. The multiverse is what it is, or isn't, regardless of how we feel about it. Our task is to understand it as clearly as possible, and then decide how to live in light of that understanding. The science will continue regardless of the philosophical implications. Researchers will keep building quantum computers, analyzing cosmological data, developing better theoretical models. The question of whether the multiverse is real will eventually be settled, one way or another, by observations and experiments. That's how science works. It doesn't care about our preferences or our need for meaning. It cares about what's true. And if the truth is that we live in a multiverse, then we'll need to adjust our worldviews accordingly. But adjustment takes time. The Copernican revolution, the realization that Earth orbits the Sun rather than vice versa, took more than a century to be fully accepted and integrated into human thought. The Darwinian revolution, the understanding that humans evolved from earlier species rather than being specially created, is still being absorbed by culture 300 years later. The quantum revolution, the discovery that reality is fundamentally probabilistic and observer-dependent, has been around for a century and still feels deeply counterintuitive. The multiverse revolution, if it happens, will likely take generations to fully assimilate. We're at the beginning of that process. The scientific case for the multiverse is just becoming strong enough to take seriously. The philosophical and cultural implications are just starting to be explored. Future generations will grow up in a world where the multiverse is either accepted fact or rejected theory, and their intuitions will be shaped accordingly. They'll find it as natural to think about parallel universes as we find it natural to think about galaxies. Or they'll know the multiverse was a wrong turn and will wonder why we ever took it seriously. Either way, they'll have answers we don't have yet. The measurements that will give us those answers are being made right now. Quantum computers are running. Telescopes are observing, particle accelerators are colliding. Theorists are calculating. Slowly, incrementally, the evidence is accumulating. Each new data point either strengthens or weakens the case for the multiverse. Each new theoretical development either solves problems or creates new ones. The process is messy and uncertain, full of false starts and dead ends, but it's moving forward. What's remarkable is that we can do this at all. We can ask whether parallel universes exist and actually make progress toward answering the question. We can build instruments sensitive enough to detect photons from the edge of the observable universe, and old enough to have been traveling for 13.8 billion years. We can manipulate individual quantum particles and measure their properties with extraordinary precision. We can simulate the evolution of universes in supercomputers and compare the results to observation. We can develop mathematical frameworks that unify quantum mechanics and gravity. These capabilities would have seemed like magic to previous generations. They're routine science now. The tools keep improving. The James Webb Space Telescope, launched in 2021, is more powerful than any previous space telescope and is revealing the universe at wavelengths and sensitivities never before achieved. Future telescopes, both ground-based and space-based, will push even further. Future quantum computers will manipulate thousands or millions of qubits. Future particle accelerators, if they're built, will probe higher energies and rarer processes. Each advance opens new windows on reality and brings us closer to answering fundamental questions. But there's also the possibility that we'll hit limits. Some questions might be unanswerable with any conceivable technology. If other universes are truly causally disconnected from ours, then no amount of technological progress will let us observe them directly. We'll be left making inferences from theory and indirect evidence, never quite certain. That's frustrating but not unprecedented. We've learned to live with uncertainty before. We can do it again if necessary. The history of science is full of questions that seemed unanswerable until they were answered. People once thought we could never know what stars are made of. Then spectroscopy revealed their composition. People thought we could never measure the age of the Earth. Then radiometric dating gave us the answer. People thought we could never observe atoms. Then scanning tunneling microscopes made them visible. The impossible keeps becoming possible. Maybe the multiverse will follow the same trajectory. Maybe it won't. We'll find out. In the meantime, we live with uncertainty and awe. Uncertainty because the biggest questions remain open. Awe because we're even in a position to ask them. You exist in a moment when science has advanced far enough to seriously contemplate parallel universes, but not far enough to confirm or rule them out definitively. That's a remarkable time to be alive. You're witnessing the exploration of a frontier that previous generations could only dream about. Think about the chain of events that led to this moment. The Big Bang 13.8 billion years ago created space and time. Cosmic inflation stretched the universe smooth and planted the seeds of structure. Quantum fluctuations got amplified into density variations. Gravity pulled matter together into galaxies and stars. Heavy elements formed in stellar cores and spread through supernovae. Planets condensed from dust. Life emerged on at least one planet. Evolution produced brains capable of abstract thought. Civilizations developed science and technology. All of that had to happen for you to be here, reading these words, contemplating the multiverse. If the multiverse is real, this chain of events happened countless times, in different ways, in different bubbles. But you're only aware of this one instance, this particular branch, this specific sequence of accidents that produced your existence. The other versions are separate and unreachable. Your experience is singular even if your existence is multiply realized. That duality, the tension between uniqueness and repetition, is at the heart of what the multiverse means for personal identity and meaning. Maybe in the end, the multiverse doesn't change anything that matters. You still wake up each morning in the same universe, make the same kinds of choices, experience the same qualia of consciousness. Whether or not there are parallel versions of you doing things differently in other realities doesn't affect your subjective experience here. You live your life in one branch, and that's the only branch you ever directly know. The multiverse is background context. interesting but not practically relevant to daily existence. Or maybe it changes everything. Maybe knowing that every choice spawns branches affects how you think about decisions and regret. Maybe knowing that the universe is one among infinite others changes your sense of significance and purpose. Maybe undiscovery opens new mysteries. If the multiverse is confirmed, we'll immediately want to know what kinds of universes exist in the landscape. Can we ever communicate with them? Can we learn anything about their properties? Are there patterns in how bubbles form and what laws they have? The multiverse wouldn't be the end of cosmology. It would be the beginning of a new chapter. And if the multiverse is ruled out, if we discover that the universe is singular after all, that will raise its own questions. Why are the constants fine-tuned if there's no multiverse to provide anthropic explanation? Is there a deeper theory that predicts them? Is there some other explanation we haven't thought of? Ruling out the multiverse wouldn't end the inquiry. It would redirect it toward different answers. Either way, the adventure continues. For now, we're in the uncertainty. The data points in intriguing directions, but doesn't yet compel. The theories are elegant, but not yet confirmed. We're balanced on a knife edge between worldviews, between seeing reality as singular or plural, between understanding our existence as unique or multiply instantiated. It's an uncomfortable place to be, but also an exciting one. This is what the frontier of knowledge looks like. This is what it feels like to push against the boundaries of understanding. So here we are, 13.8 billion years after the Big Bang, on a planet orbiting a star in a galaxy that might be one bubble in an infinite multiverse. We've come a long way from our ancestors who thought the sky was a dome and stars were lights hung above the Earth. We've learned that reality is vastly larger and stranger than our intuitions suggest. We've discovered quantum mechanics and relativity, mapped the genome and the cosmos, split the atom, and merged black holes. We've become a species capable of contemplating our own cosmic insignificance while simultaneously measuring the universe with extraordinary precision. The multiverse is the latest chapter in that ongoing story of discovery. It might be true, it might be false, but either way, the fact that we can seriously investigate it, that we have the mathematics and the technology and the observations to make progress on such a deep question is itself remarkable. We're living in an age of wonders, when ancient questions about the nature of reality are finally becoming answerable. Not all at once, not with certainty, but genuinely, incrementally answerable. If this journey through the science and philosophy of the multiverse has resonated with you, if you found wonder in the strangeness of quantum branching and cosmic inflation, if you felt the vertiginous thrill of contemplating infinite parallel realities, then you've experienced something important. You've connected with the deepest questions humans can ask. Where are we? What is reality? Why is there something rather than nothing? The multiverse might provide answers, or it might lead to new questions. But engaging with it means engaging with the fundamental mystery of existence. If you found value in this exploration, consider continuing the journey. There are more cosmic mysteries waiting, more frontiers of knowledge to explore, more questions that sit at the boundary between the known and the unknown. The universe, or multiverse, is full of wonders that we're only beginning to understand. Each one offers a chance to see reality more clearly, to refine our worldviews, to appreciate the extraordinary nature of existence. Leave your thoughts in the comments if you have reactions to these ideas, if you find the multiverse compelling or unconvincing, if you've wrestled with what it means for your own sense of meaning and purpose. These conversations matter. They're how we collectively process new knowledge and integrate it into culture. Science doesn't happen in isolation. It's a social process. and you're part of it. And until next time, wherever you are in this vast and possibly plural cosmos, whatever branch you find yourself in, whatever bubble universe you inhabit, keep looking up. Keep asking questions. Keep pushing against the boundaries of the known. Reality is stranger than we imagine, and probably stranger than we can imagine. But it's knowable, we can measure it, understand it, marvel at it. We're conscious patterns in the fabric of space-time, temporary arrangements of matter and energy that somehow can contemplate the whole. That's miraculous whether or not the multiverse is real. The adventure continues. The questions remain open. The universe keeps revealing its secrets slowly, reluctantly, but genuinely. We're part of that process, witnesses and investigators, products of cosmic evolution that have become capable of understanding cosmic evolution. The multiverse theory just got terrifyingly real, but terror can transform into awe when you give it time. Stay curious, stay wonderstruck, stay engaged with the deepest questions reality offers. This is what it means to be human in the 21st century. Balance between knowledge and mystery, reaching toward understanding while embracing uncertainty.